Okay, everybody, quiet down, please. Today is April 1st, 2013, April Fool's Day.
Nothing funny happened today, though. There's nothing that happened.
All right, quiet down, everybody. You should have your notebooks out. Thank you, thank you. Okay, ladies and gentlemen, light is a electromagnetic wave, and we're going to be taking a deeper look at to how light behaves when it strikes a mirror or when it goes through a lens. That's an important distinction. You see, mirrors reflect light. Light never goes through a mirror, it just hits the surface and bounces back. On the other hand, it goes through a lens. Light goes through a lens, and lenses cause light to bend. Okay? So that's an important distinction I want you to know between these two. And how they bend or how they reflect is actually an entire field of science called optics. You could actually get a degree and just spend your life doing optics. That's a job field. So it's interesting how all these little, like, it seems like a small piece of science is actually an enormous field. So let's make sure that we know the difference between mirrors and lenses in the notes. Correctamundo. Light passes through lenses.
You look at yourself in the mirror.
You can figure it out. Well done. Light passes through lenses, however, light reflects off of mirrors. Now I'm going to underline the word reflects because there's another word that means to bend that I need to add to the bottom definition. See, you expect mirrors to reflect light and you expect lenses to bend or refract light. Can you see? Because there's space up here if you need to sit closer. What's your question? One-way mirrors? See, that's a misconception. That's a combination of a mirror and a lens. That's a great question. So it reflects some of the light, actually most of the light, because it seems like a mirror from one side, and from the other side, light passes through it, so it's a lens. Okay. I don't think we're going to have time to get to lenses today. We're going to talk mostly about mirrors. Where are your notes, sir?
No, I knew it.
Well, that's fine. We're about to get into things you don't know. All right. There are three shapes I need you to know. The first shape, this is the geometry of these things. The first shape of a lens or a mirror that you need to know is going to be a flat surface, which is called planar. Whenever you see a flat surface, it is planar. The next surface I want you to know about, shaped like a cove, is called concave. I put a little red arrow indicating which direction the light was coming in, because the next one, does anyone know what the name of the next one's going to be?
Yeah.
What is it? Nope. It looks like this. Outcave, that's a good guess, but convex is the correct term for this type of mirror or lens. Now, it's important to also keep in mind that these are solid things, okay? It's not just a line, it's got some volume to it. So to correctly draw a mirror that's planar, I kind of do that like this, okay? Just to show that it's solid. So far, so good. Is everyone with me? Couple of different things I need you to know. I'm sort of giving you the foundational stuff before we actually get into it. Mind taking your hat off, sir? Thank you. All right. Through the use of mirrors and lenses, we can make things appear smaller. We can make things appear upside down. No, that's completely wrong. We can't make things appear around. but we can make things appear bigger, smaller, upside down, right side up, and some other things. So these are optical terms. And for example, bigger or smaller, we call that, starts with an M. Magnification. Okay? So if we start out with an object which is large, and we make the object smaller through optics, that's a smaller image. So that's a form of magnification. It's basically, it seems to be opposite type of magnification, but it's magnification. But we can also take an object which is small and make it bigger, which is often useful too. What does the sign in a mirror on your car say? Thank you. Objects may be closer than they appear. The mirror on your car is making objects larger into images which are smaller. Your mirrors on your car are doing reverse magnification. Does anyone know why? It is cool. Why is it more safe to have your mirrors do reverse magnification?
Gives you like a full view of what's behind you.
Yes, you get a full view of what's behind you. Ladies and gentlemen, your mirror is this big. That's not very big. However, because it happens to be a special type of mirror, it gives you a broader, wider view of what's behind you. So to fit more stuff into such a small mirror, it makes everything smaller. Okay? So it's reverse magnified to give you a wider view. Okay. What's an example of when you would want to make something bigger? Something small to make it bigger. What's an example? Magnifying glass. What else? Glasses. What else? Microscope. What else? Telescopes. There's a ton of applications where we want to make small things into big things. It lets us see worlds, for example, that we are not used to. A magnifying glass to use to look at fingerprints. A microscope to look at little bacteria swimming around in your pond. A telescope to look at the surface of the moon. Okay? So magnification is nice. The next thing I want to show you, this is obvious. Optics allows us to do this too. Here's your object. Object. And here's your image.
What submarines have?
Periscopes? No. It's a little different. This is, ladies and gentlemen, the difference between right side up and upside down. If the image was on the top, like so, this would be right side up is the correct term for it. Right side up. And if it's down here, it's called upside is down. Okay? When you are describing what your optical system does, you're going to have to use this terminology. Sometimes I'm going to ask you, is it right side up? Is it upside down? That's what I mean. I don't think we need to talk about this too much. Has anyone ever seen their image flipped upside down in a mirror? Look into a spoon sometime. See what happens. A spoon. Because, ladies and gentlemen, spoons, if they're shiny enough, should allow you to see this phenomenon. It's pretty cool. If your spoon's all scuffed up, you might not see a good image. Okay, finally, the last one's a little weird and is completely outside of the realm of what you guys have experienced in your everyday lives. But Alice in Wonderland is a story about a girl who sometimes looks through a mirror and imagines if there's a world on the other side of the mirror. You may have done this if you have a hallway mirror as a kid. Sometimes kids sit in front of it, look through, and they're like, man, it's just as if, especially a clean one, it's just as if like I can go around the corners and go into the room that's on the other side of this mirror. Okay? It's as if you're looking into something that is behind the mirror. In fact, one of the books of Alice in Wonderland is called Beyond the Looking Glass. So, There is a scientific term for this. Let's say you've got an object, okay? Little person, okay? Here's your mirror. Okay? The person is looking into the mirror. If it appears like an image is behind the mirror image, we call this whole thing imaginary. That's the key word. That's the scientific term for what it means when the object creates a reflection which appears behind the mirror. It's imaginary. However, there is an opposite to imaginary. If you're looking into a mirror, it's curved, and you look into the mirror, and here's your object, OBJ for object. It's short term, abbreviated. And your image appears in front of the mirror. Here's your image. Notice IMG for image, shorthand. This is called real. Real means your reflection is on the same side of the mirror as you. Okay. Those are three characteristics of images and objects and mirrors, and now it's time to get to the physics. We're going to apply them all and have a look at some mirrors and figure out how this all comes together in something which is called lens diagrams. We're going to draw some diagrams. Now, before we start, I think we need to get some equipment. I would like you all to go get a ruler and 2 colored pencils, different colors, please. All right, the strategy here is you're going to use black and white for everything except for the light. When you get to the light rays, you're going to use the colors. So I'll change colors on my whiteboard, and you'll be able to as well. All right, the first type of mirror that we're going to be drawing a diagram for is going to be called a planar mirror. It looks like this to start off with. Kind of like wave diagrams, we're going to include an origin. That's the line in the middle. This is called the origin right here. Okay, I'm going to put an object over here and label it O. What does O stand for? Very good. All right. The first ray of light, I'm going to use the term parallel. That means it's going to go in the same direction as the origin. I'm going to draw a ray of light which is parallel to the origin. And when it strikes the front surface of the mirror, it is going to bounce directly backwards. So it's going to go towards the mirror and then back again. However, I would also like you to include a dashed line that goes behind the mirror forever, staying parallel, like this. Dash, 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 dash. Colored, all color. I'm going to give a couple people some time to catch up. I'm going to just walk around, make sure everyone's doing the right thing. Good. Keep that colored. Good. Dash line, please. Yep. 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 Looking good. Okay. The next line, there's only 2 lines on my ray diagrams. Ladies and gentlemen, eyes up here again. There are only 2 lines on my ray diagrams. In physics, you might draw 3. So we're starting off with a simple, and later on in school, you'll do them a little more complicated. But the second line that I would like you to draw is going to be making a line from the same point here to this point here. Notice this is the intersection of the front of the mirror and the origin. So the line goes in, and then it bounces off at the same angle, like this. The second color, yes. In addition, I would like you to do a dashed line like so. It basically, you see how this line goes straight, 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 hits this intersection? After that, I want you to do a dashed line like that. You go toward the origin, this intersection, and then you make an angle of reflection, which is the exact same, so just sketch it. But then you also go backwards with a dotted line. I'll show you. I'll show you why. This is weird science here. Who needs help? Okay. If you have this, I'd like to show you how to finish it. Okay. So the reason that we had to go behind the mirror is because, like Alice, we are looking through the looking glass. We are creating an imaginary image. When you look into a flat mirror, it looks like your body, which is the object at which you're looking at, is inside of the mirror. And it looks like it's right here. It's going to be the same size. This is, by the way, the image. It's going to be the same size. It's going to be right side up. And look, it's on the wrong side of the mirror. It's behind the mirror. That's impossible. So it's called an imaginary image. It is not real. It's only imaginary. The light does not travel through the mirror. That's a property of mirrors. The light bounces off the mirror. However, it works in a different fashion. It seems as if it's behind the mirror. But that's just a figment of your imagination. It's weird. Okay? I hope I'm not upsetting anybody, because it's time for our next type of mirror. By the way, this title for this diagram is planar mirror reflection. Okay. Now, the best part of a spoon, and I'm so glad that somebody mentioned it, the best part of a spoon is it's got two types of mirrors on it. If you look inside the bowl of a spoon, we call that a what type of mirror? Concave is right. And if you look on the back of a spoon, we call it convex. Very good. So you can do a little bit of an experiment with these two types of mirrors using a spoon. Let's first start with the concave. Okay, here's a concave mirror. Draw it as best as you can. In addition, for your concave mirror, it's like the Death Star, in which it focuses all of the light to a point, which we call the focus. So just choose a point in front of the mirror to call the focus. Here's a fun fact. If you have a big enough concave mirror and it's outside, you can start fires with it. It focuses the sunlight to a single point, which will be very, very hot. That's true, but that's a type of a lens. When it comes to mirrors, the type of mirror you want to start a fire is called convex mirror. Or, sorry, concave mirror. I misspoke. So let's put that fact down here. Starts fires. And I'll show you why. All right. Let's again draw a little person here. And because we want to be fair, let's make it a girl type person. Let's give her some hair. There you go. She's happy. Okay. Ladies and gentlemen, let's start with our red ray of light. What happens? What does it do? Well, the red ray of light is going to be parallel to the origin again. It's going to travel straight from the top of her head towards the mirror and strike the mirror like that. And then the mirror is going to work its magic and focus the light into its focus. Okay, what's that mean? That means it's going to go straight through the dot, like a laser. No matter where a parallel light ray hits, it will be focused to that point. Sorry? Yeah, that star is just like a special thing to know about this type of mirror. Now, the blue light. We're going to go through the focus. We're going to kind of go backwards. It goes through the focus to begin with. So you're going to connect a line that goes from here through here. Connect those points with your ruler. Strikes the mirror. And then it gets sent back parallel to the origin. Like so. That creates an intersection, which is what we were looking for. And the intersection is where the image is. So, I'm going to take this girl, copy her. You can't do this. I can do this. And actually, I'm going to clone her. Wait, she turned into a man. Now he or she. Hey, that's awkward. What's going on over here? Cancel this nonsense. There we go. Now, sorry about that, girls. Still equal opportunity. Gonna make her a girl, but now she's sad. Okay, there we go. You're gonna notice she's what? Is she right side up?
No, upside down.
If you look into a concave mirror, under most circumstances, your image will be upside down. So when you look into the spoon, you should be upside down. Upside, or a metal bowl, that's right. Upside down. Must be that whole imaginary world coming at us. Okay, the image is upside down. Shh. The image is also going to be smaller. If you look at yourself in a spoon, your head's not going to be this big. The image is smaller. And ladies and gentlemen, is your image in reality, in the real world? Is it on the correct side of the mirror? Yes, your image is on the same side of the mirror as your object. So it's a real image. It's not imaginary. It's not a figment of your imagination. True. I'm telling you, it's true. Why would I? Well, now that he's 16, he obviously knows everything.
He knew everything when he was 15.
He knew everything when he was 15? So is he learning more or is he forgetting stuff?
He's forgetting.
He sleeps on a dictionary, yeah. Hey, I have one more mirror type, if you're ready. Last one. Convex mirror, that's right. You ready for the convex mirror? Good, turn the page, please. Okie dokie, let's do it. Last of your notes. Sorry for hitting your funny bone, Ariana. Okay, convex mirror. Okay, everybody. The focus of the convex mirror is going to be on the other side of things. Let's do it. Here's the person. Their first ray of light is going to be parallel to the origin. And then you're going to make a this is part you're gonna have to look up because I can't word describe it without you seeing what I'm doing. Take a look, please. You're going to connect this focal point and this point at the surface of the mirror. You're going to go up with a dotted dashed line to connect the two until you reach this point in which it becomes solid. Because this ray of light reflects off like that, and it's going to cast an imaginary line backwards. All right.
I keep missing it.
I'm going to email. I'll email the administrators to let them know that there's a light. All right. Back to the notes, folks. The blue line is going to head toward, from the top of the head, it's going to head towards the focal point. So it's going to go straight. And now at this point, what it's going to do is it's going to bounce and stay parallel to the origin. I'm going to go backward with a dashed line that's also parallel to the origin. Does anybody need help? Okay? So it's going to head as if it was heading straight towards this focal point, but it gets intercepted when it strikes the front surface of this convex lens. It's going to reflect back parallel to the origin. Yes, sir.
Are those the mirrors that make you look like really okay?
Let's take a look what they make you look like.
You have one?
Yeah.
No? But we're going to look at the diagram to figure this out. Ladies and gentlemen, your intersection is here. Therefore, you are there. What does it do in terms of magnification? Image is smaller? Nope. It's smaller in every dimension. So it should be the exact same size and proportions as you, just smaller. The image is smaller. The image is imaginary. And finally, the image is upside up. Yep, right side up. Both mean the same thing, just different ways of saying it. Ladies and gentlemen, this concludes our notes for the day. I'd like you to take a 2-minute break, and then we're going to talk about wheels. Done with notes.